Hey guys, so I'm making this video just because of the last session. These are my first time seeing these problems, so be patient and we can practice them together. The first question says, consider a solution initially containing 0.4 moles of fluoride anion and 0.3 moles of hydrogen fluoride. So I think the best way to do these is imagine them. So this is like a beaker and it has some anion in it and some HF. So what we see is these are the two things in here we know for sure. And they're probably like in equilibrium with each other. And it even tells us the amounts. Then it says how many moles of hydrogen fluoride are present after addition of 0.2 moles of HCl to the solution. So basically when you're adding, well, what are we adding first of all? We're adding a strong acid. So this is pretty much a buffer being tested. So a buffer is anything weak, either a weak acid and its conjugate or a weak base and its conjugate. Okay. And then we can add strong acid to them or add strong base to them. And then hopefully the pH won't change. If we add too much of something strong though, the pH will eventually change. In this case, we're adding a strong acid. So what you want to imagine is what matters. The Cl, it goes in as well, but it's not what matters. What matters is that we're adding something acidic. So the H plus is going to go in. H plus is going to react with the only thing it can react with. It's not going to react with the HF, but it will react with this fluoride anion. Because what you need to remember is this is a basic anion, right? It's a basic anion because it's the conjugate of a weak acid, because conjugates of weak acids are basic anions. Okay, so that means it can take the proton, which is what bases do. So it says how many hydrogen fluorides are present after the addition of 0.2 moles of HCl. So let's just take the initial and add it to the new amount that's made. So the initial is here, it's 0.3. So anything that's basically under 0.3 will be wrong, and equal to 0.3 will also be wrong because that was our initial amount. We know it should be above that because this is our initial, and then more is going to be made when it reacts with the hydrogen, right? It's going to shift this way as it reacts with the hydrogen. So let's see how much HCl was added, 0.2. Since this is a 1-to-1 ratio, one H plus and one F minus is needed to make one HF. We know that 0.2 moles of HCl would make 0.2 of this H plus, and we have 0.4 moles of hydrogen fluoride. So, I'm sorry, 0.2 moles of the fluoride. This is, I know this looks like hydrogen fluoride. This was a plus sign. And we have 0.4 moles of this. So what we're going to get is 0.2 out of this 0.4 is going to react with it, right? Because H plus is our limiting reactant here. And then we're going to get 0.2 of this guy, and then we'll have like plus 0.2 left over of the F minus. Sorry, it's kind of messy, but that means we can just add 0.2 with the original amount 0.3, and the answer should be 0.5. So that's how you do these. Okay. So let's go to the next one. All right. So the next one here, consider a solution initially containing 0.4 moles of fluoride anion, 0.3 moles of hydrogen fluoride. let's see what the rest of it says. How many moles of hydrogen and fluoride are present after adding 70 mils of 0.6 mole per liter HCl? So at first it's like, how do I do this? Where do I start? Because there's so many numbers. But this is actually the same exact thing as above. The only thing it needs is some dimensional analysis. So let's make like a new beaker. So we know we have 0.4 moles of this anion, and then we have 0.3 moles of the HF, okay? And they're chilling in the beaker. And then it says how many are present after we add some amount of HCl. So that's how we know this is the same thing. We don't know the amount because they gave it to us in a not clear way, but we do know at this point some strong acid is being added to this weak acid solution. So, and we know it's gonna react with the only thing it can react with, which is the anion, okay? That's basic anion, okay? So we just have to find the amounts and we can use the same thing as before. So basically what we're given here is 0.6 mole per liter is the concentration of the acid. So maybe we have some acid and like a bucket and it's like 1 liter of it or whatever. And we know that there's 0.6 moles per liter. But like you're not going to pour this entire bucket in here. That would be way too much. You just want to take a little bit of it. So you take about 70 mils. Okay. So when you just like put these numbers next to each other, you can tell what needs to be done, right? The volume needs to cancel out so we can get moles. But this volume is not in liters, it's 70 milliliters. So to get it in liters, we're just going to divide it by 1,000 and then multiply. So 70 divided by 1,000 times 0.6. I think that should be something, let's check it out real quick. Okay, so that's 0.042 moles. So that's how many moles of H plus were added. So how many moles of fluoride do we have? We have 0.4. So we have more than enough to combat the effects of this acid being added. And that's the point. We have not reached our equivalence point yet because we have 0.4 of this, and then it's going to react with the H plus, which is 0.042 is the amount of it. And we're going to get, let's put the HF here. We're going to get 0.042 for our new amount of HF. And then the F minus is going to be whatever 0.4 minus 0.042 is. Because once the F minus reacts with the H, it turns into something else. So we have to make sure we notice that the anion goes away, even though the question isn't asking for that. So this is how much of this weak acid we've created. And the original amount that we had of the weak acid was 0.3. So 0.3 plus 0.042 is gonna be this guy. This is how much HF we have. And actually, the question did ask for the amount of fluoride. So I'm guessing it's this C. Okay, so probably you have to put this in your calculator to confirm, but that seems right. So the point here is to notice that because we haven't reached our equivalence point, this solution is not going to change pH too much. You start to change pH drastically once you no longer have some type of conjugate to react with the acid that was added. So right now we still have this F minus that's making weak acid. And remember, weak acids, they don't lose their hydrogens that much. Therefore, as long as the F minus anion, the fluoride anion grabs onto the hydrogen, this buffer is going to stay at a non-acidic place. But as soon as all of it's wiped out, for example, if we had 0.4 of the H plus, or let's say we had 0.5 of it, what we would get is actually 0.4 of the hydrogen fluoride, because the limiting reactant now would be the fluoride anion. And then we would get 0.1 of the H plus. So here's the H plus, because now this is the leftover guy. And when this is the leftover guy, that's when you know you have an acidic solution, because nobody is absorbing that guy. It's like you have a spill on the floor and you only have a certain amount of paper towels. If you have like a small spill, then you can absorb all of it. But if you have a huge spill, you're going to be able to absorb some of it, but then some of the spill is going to stay. And that's the same concept. Buffers are just like these absorbing anions and cations. So let's go on to the next question for more practice. So here we go. Let's go to the next one. 35. Consider a solution initially containing 0.5 moles of ammonium and 0.3 moles of ammonium ion. So once again, best thing to do is imagine. So here's our NH3, our ammonia, and we know it's like in equilibrium with the ammonium. So this is like a weak base situation. You can also see it as a weak acid situation, whichever one. But point is the hydrogen is exchanged between, so we have a buffer. So that means if we add a strong base or strong acid, we should not see the pH go up by too much unless we pass the equivalence point. So now let's see, it says how many moles of ammonia and how many moles of ammonium ion are present after we add some amount of base. So in this case, we're adding OH ions. That's what's important. We're adding OH minus. So this solution would become basic if we don't have the proper amount of what to react with it. Is the ammonia going to react with it or the ammonium? Now that's the other question. So since this is a base, it's different than acids. In acids, we have some type of conjugate anion take the hydrogen, and once it does that, it becomes this HX. Now in bases, you have to know it's a little bit like the other way around. What you basically have here is you have to know that it will react with the thing that is the acid. So instead of this is the conjugate base, it's going to react with the conjugate acid, which is our ammonium, right? Because if you look at this buffer, you have to figure out, well, which one is the acid, which one's the base? Well, the one that has extra protons should be the acid. So this, what's going to happen is the base here, the OH minus, is going to take the hydrogen from this guy and become H2O, right? And we can just make it simpler and not even put H2O. We can just put, we can call our conjugate acid AH, or HA, I guess is how people write it. And then the base OH is gonna take the hydrogen and then become H2O. Okay, so that way you can see that the base always takes a hydrogen no matter what the acid is, NH4 or whatever. So that's what we create. So in this case, we created H2O, but it's the same concept. So then it says how many moles of ammonia and how many moles of ammonium ion are same concept. So just as long as you understand that. So what we want to know now is we see that we have this much 0.3 moles of ammonium ion to react with this new incoming base. So we have 0.3. So now we just need to know how much of this OH minus is going to react with it to be basically neutralized, so the basic properties of the solution don't go up. So what we're going to have to figure out is how much this is. So 0.8 moles per liter And then we're gonna wanna find out how many moles there are. So let's put 40 over 1,000. That's gonna be our liters. And then now we can do this. So let me find a calculator. I think calculating will be a little faster. Okay, so 0.032 is the amount of this NaOH, and the amount of NaOH is going to be equal to the amount of OH minus. So now, since the OH minus is our limiting reagent, we're going to get, well, NH3 equal to 0.3 minus 0.032, and then plus H2O equal to 0.032, right? Okay, so now we should know the amount of this present, our NH3. It should be 0.3. Well, I guess this one's none of the above. Let me check the answer key. Oh, 35 is A. Let's see where we went wrong. Okay, I see where I went wrong. My bad. I used the wrong thing for. Okay. No, actually, I didn't do it wrong. I did it correctly. The only thing is, so we made 3 minus 0.032 of the ammonia, right? So let's calculate what that is. 0.3 minus 0.032. That's 0.268. 0.268. But I was looking for 0.268 here because I forgot there was already some ammonia in the solution. So you have to remember that. So actually it's going to be 5 plus, that's still not really right. Let's see. Oh, I'm sorry. This is ammonium. See, it's kind of tricky. This is ammonium, but so you have to write ammonium here. So we just calculated for the amount of ammonium, which is 0.0268. Hopefully you guys caught that mistake I made. And then the NH3. Okay, now let's calculate that. There was initially 0.5 of the NH3, but now there's going to be a little bit more. And the reason that there's going to be a little bit more is this. Yeah. So when this ammonium gives its hydrogen away to OH minus and creates H2O, you have to recognize what it becomes. What it's going to become is the NH3, right? So here, this NH4 plus reacts with this, and then we know that the amount becomes less because every time it reacts, it loses this much. And then when the hydrogen goes to the OH to make the H2O, but it becomes something in that process. So that thing that it becomes when it loses it is going to be NH3. Okay, so this one was a little bit tricky, but we got through it. Okay, let's go to the next one. Okay, consider a solution initially containing 0.4 moles of fluoride anion, okay, and 0.3 moles of hydrogen fluoride. What is the pH? Okay, so now we're solving for pH. What is the pH after addition of some amount of acid? And it gives us the K and everything. So what you have to know here is what equation you're going to use. So basically in the past, what we've done to find pH is taken the, oops, yeah, so HA would be here, and then I guess I should write it like this. HA is on the bottom, and then the amount of H plus and A minus is on the top, and it equals like the Ka, and we would be given something like our Ka and this, and we could figure out the H plus and take the negative log of it. So then we would have the pH. But in buffers, we can't use this equation. It's not that simple. You have to be able to recognize when your problem is using a buffer, because then you have to use the Henderson-Hasselbalch equation, which basically says pH is equal to pKa plus the log of A minus over HA. Let me just confirm that real quick. Henderson-Hasselbalch. Yeah, so that's the right equation. So this is the equation we have to use, and it's actually not that bad of an equation to use. What we recognized first that it was a buffer. Why? Because hydrogen fluoride is a weak acid, so we know it's a buffer. Okay, so and the Ka that goes here is always the Ka of the buffer. So the Ka of the weak acid here. So here that's 7.2 times 10 to the negative 4. And then what's going to go here is negative log, because P is the symbol for negative log. P equals negative log. Okay, so far we got a lot of the equation down. So let's write the rest of the equation. Plus log of the conjugate over the acid. So now we basically see that we only have to solve for one thing. There needs to be a number here, and we don't know what this number here is, but we know that it's equal to A minus over HA, the conjugate over the acid. So our acid is this, so the conjugate must be F minus. So let's go ahead and just draw the little reaction. This is, we need to find the amount of each of these and plug them in. So it said initially it has 0.4 moles of fluoride and then 0.3 moles of HF. And then we add 0.2 moles of HCl to the solution. So what I like to do is when I write an acid being added or a strong base being added, I like to deal with one thing at a time. I don't like to deal with the whole thing because it's too complicated. I only like to deal with the guy that's going to react with it. So I'm going to kind of ignore the HF and draw a new thing. Like this is what we've been doing in the other problems. Just write the F minus, the 0.4 amount plus whatever amount of HCl is added. And if you want, you can add HCl, or you can just put H plus. In this case, I'm going to write the whole thing because above I was writing just the H plus, so you guys can get both experiences. So it's at 0.2 of the HCl. So since the limiting reactant here is the HCl, what we're going to make is HF equal to 0.2, okay? And then our new F minus concentration is going to be 0.2, right? Because 0.4 minus 0.2. Oh man, I should have, let me rewrite this so there's a lot more room. So HCl here, F minus here. We have 0.4 of this, 0.2 of this. They're going to react head to head. The HF concentration is going to depend on the HCl concentration. So we're going to get 0.2 of the HF. And then the F minus is going to go down. So we're going to have 0.4 minus 0.2 because every F minus reacts to create something new. So we're going to lose 0.2 of it. So I can already tell you what the final amount of our conjugate, our A minus is. It's going to be 0.2. Okay. And it seems if you try to do this too fast that we have the HF amount already, but we don't. We need one more step. So, and then here's the thing I haven't been doing in the previous ones. if you really want to, just you can write the Cl minus concentration, it will be 0.2, but really you can just ignore it and write the H plus like we've been doing above. So now here, we're not going to put 0.2 just because 0.2 was made. 0.2 was made, but that's the new amount. We already had 0.3 in the solution. So this is where a lot of people mess up. It's going to be 0.3 plus 0.2. So we're basically going to have 0.2 over 0.5. Okay, so 2 over 5. So now you can just plug this into a calculator. And unfortunately, I do not have a very good calculator right now on me to solve for this, but I can tell you one thing. You guys can solve for it yourself, but I can tell you that I know that this pH is not going to be, it's not going to be too far off from the pKa here, okay? And that's kind of how buffers work. So the pKa is similar to pH. It's a measure of acidity. And then the point of buffers is this part here should be plus or minus 1 or plus or minus less than 1. If it becomes something bigger than that, like 2, 3, we've broken the buffer. And that would only happen if we've put enough acid that can react with all the fluoride anion. And here it hasn't. We only had 0.2 of this, but we had 0.4 of this. The buffer wasn't broken. We would have to have 0.4 and more to pass this equivalence point and break this buffer. So that's how I knew that this pH would be only one, it would be less than 1. Basically, in this case, since it's becoming more acidic, we're going to have a minus sign here. So the math will give you the minus sign, but I can tell that it will be a minus sign because we're adding an acid, therefore the pH has to go lower, but not too low. And yeah, so this pKa here minus something that is less than 1. So less than 1. Okay. You guys can do the rest of it here. I think that should be good for now. Yeah. All right, then that's it for this video. You guys can email me any questions you have. And yeah, have a good night, everybody.